you very much being here so early. So indeed, the original title of the lecture was including MBL and something beyond, and I hope that something beyond probably wouldn't fit in these lectures, but something beyond maybe will fit in my research talk about other possible mechanisms of avoiding thermalization. And I decided to kind of try to devote the lectures solely to many-body localization, and in the end of second lecture, if time permits, hopefully I'll have some time also to discuss open questions and bring a bit again to the questions on which probably some people in the audience are doing research at this moment. Otherwise, tentative plan is I will start with a brief thermalization review, and I know that thermalization was already reviewed in several talks, still maybe not gonna hurt too much. Then I'll briefly mention what is Anderson insulator, right, and discuss early ideas of how to obtain stability of many-body localization from Anderson. And finally, after that, I'll go somewhat in depth into exploring properties of many-body localized phase, in particular this phenomenological picture of local integrals of motion in it. And finally, again, number 4, if I have time, I'll try to get either to discussing how we can probe transition and basically prepare the base for tomorrow's lectures by Roman, which are going to be somewhat devoted to many-body localization transition. And again, if time permits, maybe flow cam. But let's see how grossly I overestimated the times that I need. So let me start again with thermalization. And the basic context, I guess everybody is on the same page. We have isolated interacting system. We have some non-equilibrium initial state, right? And then we follow intrinsic evolution of our system, right? We have, for example, quantum quench. Not necessary. And we ask what is the fate of our system, right? Again, using intuitive notions, if we start with a classical system, they're reaching equilibrium and ergodic properties, right? Or possibility of system to explore all possible configurations, constrained maybe by one or few conserved quantities, right? At least intuitively for physicists are very often used synonymously. Again, I know that ergodicity is a tricky concept and proving ergodicity is a challenging matter, but again, the idea would be that you can see. So if you have the notion of ergodicity, that over course of evolution, all configurations with, let's say, E equal constant are explored, right? This intuition suggests us, right, that the system is going to spend most of the time in the most probable configurations, right? And that's, again, that's a route to thermal equilibrium. Now, in a quantum system, and I'm dealing here with many-body quantum systems, right? We have this monstrous Hilbert space, right? And we have in some sense, the issue that we have a huge Hilbert space where our evolution is to some extent trivial, right? In a Hilbert space, we have just a huge unitary matrix which rotates our vector on the one hand side, right? And that is linear operation, right? And linear operation by definition doesn't admit proper notions of chaos and proper notions of, if you have two vectors at a certain angle, however long time evolution you are doing, these two vectors are going to stay at the same angle relative to each other, right? So in that sense, you need to go a bit more to define what do you mean by thermalization and what do you mean by chaos, right, in a quantum system. And just to start with the specific examples, I will be using some one-dimensional examples just to set some Hamiltonians, right? For example, fermionic Hamiltonian, which is very often used in the studies of thermalization and also many-body localization, is fermionic chain without spins. I add interaction, maybe with periodic boundary conditions, doesn't matter for this talk. And I have some chemical potentials, which would allow later to add disorder, right? Or, again, some people who more like spins can have the same chain, right? They can have J perp, sigma plus I, sigma minus I plus 1, plus HC, plus have some JZ, sigma ZI, ZI plus 1, right? And then we would have HZ, I, I. And these are two Hamiltonians that kind of you can use to set some specific intuition about what your system can be, mappable onto each other by Jordan-Wigner. So in some sense, largely equivalent models, model of some nasty Jordan-Wigner strings, right? And then again, in the language of this specific Hamiltonian, I start with some initial psi of 0. I wait for some time, right? I get IH, for example, fermionic Hamiltonian T psi of 0. That's my, again, that's some basic notations, psi of T, my quantum evolution, right? But if I expand it over eigenstates, not much is happening, right? If I expand my psi of 0 over eigenstates, it's going to be some combination of A alpha, alpha, and this alpha are any body eigenstates say, right? And with energies E alpha, I know what's going to be my psi of T. Right? They're going to be just rest guys. And in this evolution, again, as I promised to you, there is some phase accumulation. All overlaps are going to stay constant, right? So in some sense, it's interesting that the probability to be in a given eigenstate will never change in the context of my evolution. So now how can I reach a terminal state, right? And we can try to say that system reaches a terminal state, right? If all observables here look terminal, right? So right now, again, I'm coming basically how possible way of defining thermalization, right? And I'm not formal here. I'm trying just to give an intuition about these things, right? Psi of T thermal if at long time say O of T quantum, right, which is defined as basically psi of T O, where O is some operator. The O can be equal sigma Z I, or if you want, can equal energy density Hi I plus 1, right, where this is part of the Hamiltonian which operates on two links and so on, right? So I want this quantum expectation value at long times, maybe if I'm generous at equal infinity, right? Which again, I can define this thing as being a limit 1 divided by T of integral dt, this O of T. Right? So I can define T equal infinity expectation value as such a limit. And if you think about what this limit is doing, right? Here I can open psi over all my eigenstates, and it's going to be a lot of oscillating terms when I have eigenstate alpha and eigenstate beta and of diagonal matrix element. And if I'm in a generic many-body system, energies are non-degenerate, E alpha is never equal E beta, right? And what I'm going to end up with basically sum of P alpha expectation value of my observable over my eigenstate. Right? And again, P alpha is basically my eigenstate psi of 0 value squared. Right? So that's my quantum expectation value of the Hamiltonian at long times. It's not visible, let me know. I hope, again, whole range of the blackboard is visible. And now what I want to say, right, that I want for, let's say, sub-extensive observables, right? I want for observables which are less than certain fraction of my system, And that's again also something that is a subject of research. Would it hold for all observables? Would it hold for observables which are again like 1/4 of my system or half of my system? But I want that all this, right? So I want this to be some sort of smooth function which depends only on conserved quantities. In this case, maybe energy, maybe also particle number or total spin number, right? And that would be kind of our canonical expectation value. And again, what I mean by macrocanonical expectation value is going to be basically trace of raw thermal, right, times my object. And raw thermal is a minus beta h. It's a given density metric, so we know how to calculate this quantity, right? So now again, I try to explain what I mean by thermalization, right? Or how would I try defining, leaving aside a lot of subtleties, what does it mean for a quantum system following its unitary evolution, being absolutely isolated, still to reach a thermal state. Now, question is how to ensure this, right? And that's something, again, I'm sure you heard a lot in these lectures, is so-called eigenstate thermalization hypothesis, right? So that's, again, so far was a sort of a definition, right? So now root thermalization eigenstate this. And in some sense, eigenstate thermalization hypothesis, right? You may view it as if you accept that P alpha never change, right? So probability to be in a given eigenstate is a constant of motion in a quantum evolution, right? One possible way of ensuring that all expectation values at long times are going to agree with the thermal ensemble is to say that we need thermal properties already in my eigenstates, plus I need to make sure that I cannot prepare some unreasonable combination of my eigenstates, of course, right? Then the idea would be that, again, this is sufficient route to thermalization, right? We don't have a proof about this mechanism being necessary, right? But again, I will use this as a sufficient to ensure thermalization. And what I want actually this, right? So I want now quantum expectation value of my operators. So now in many-body eigenstates to agree with the same microcanonical ensemble at a given density. Now again, it's sufficient, but we don't know if not necessary, right? Because in many cases, we have the intuition of many-body eigenstates being sort of useless, right? First of all, in the physical system, it includes this exponentially large Hilbert space. Therefore, these eigenstates are, in many cases, are practically impossible to prepare, right? Or if you think about, even if you're like magician and can do whatever you want to your quantum system, still it's going to take you exponentially long time to prepare a given eigenstate. So in some sense, you may think that you're going kind of to a too fine level, right, by requiring this, but yet many cases when you check this numerically, indeed seems that kind of systems thermalize according to the ETH, right? You take a system which thermalizes and you check properties of its eigenstates and you see that indeed all the characteristics agree, right? Again, and this would be enough, right? We need concentration of P alpha near certain energy, right? Because again, if I prepare superposition of states of an eigenstate at energy minus 100 and energy plus 100, right? And that energy would scale extensively with my system size, it's not going to be reaching thermal equilibrium in this sense, right? But that's actually, again, it turns out that such state is very hard to prepare. And you can show that if you have if you're doing a local quench, sorry, even if you are doing a global quench of your Hamiltonian, right? But if you have a local Hamiltonian, that eventually you would get a reasonable distribution of these P alphas, right? We need concentration of P alpha near certain energy, right? I need some bound on their fluctuation, right? We need a bound on the distribution of P alpha, but again, such bound can be made at least for physical initial setups. Now, this says that we are reaching thermal state, but doesn't say how we reach it, right? Because, and that's also actually quite practical question, right? You take your system, you start measuring how long do you have to wait to see that this holds with a reasonable precision. Or even so, if you see this holds with reasonable precision, there can be always fluctuations, right? So what can we say about these fluctuations? Can we bound them or no? And for fluctuations, right, you understand that for dynamics, at t not equal infinity, you cannot do this trick, right? You cannot do t equal infinity averaging. And what is going to happen is that not only diagonal expectations value of your operator are going to enter, but also off-diagonal expectation values of your operators will enter in the dynamics, right? If I write O of t at finite time, there's going to be all of diagonal matrix elements, right? So again, if you want to bound fluctuations, and again, it's not necessary to the best of my knowledge, but it's a sufficient condition, right? There is this so-called, I would call it Srednitsky ETH, and that's for all matrix elements now, right? I was asking about some diagonal matrix elements, right, for matrix elements of my operator, right? And I can write it concisely. The first term I already wrote, delta alpha beta, this classical microcanonical expectation value, right? And the diagonal part. Now, new part here is this. It's single shot I introduced heck a lot of notations here. So again, this is diagonal matrix element, this off-diagonal matrix element. So R alpha beta is a normal random number, normal distributed random variable, right? And now interesting notions are E here, which is average energy of my eigenstates, and omega, which is a relative energy of my eigenstates, right? And this guy is thermodynamic entropy. And in the simplest case, when I'm acting at the middle of my many-body spectrum, you can think about this as being 1 divided by a square root of a Hilbert space dimension, right? So again, for a spin chain at the most excited states, right, it's going to be log 2, right, times my system size. So this guy, actually, again, it's not entropy density, right, but it's thermodynamic entropy itself. Or if you want density, you must put in there a system size, right? Yes. So exactly, that's something that I'm trying to, yes. So I'm going there, and indeed, so this kind of looks somewhat surprising, right? You say that this factor, right, is exponentially decreasing in my system size, right? So we want actually all of the diagonal expectation values of my matrix elements to be suppressed, and the bigger system size you have, the more suppressed they should be, right? And you know, in some sense, kind of very rough intuition, right, about this whole ansatz is that this is roughly speaking a random matrix theory, right, extended to a local Hamiltonians. And if you recall what's happening in the random matrix theory, right, if you have two random vectors of a random matrix, which is again your Hamiltonian, right, operator is some other reasonable matrix, right, but it's normalized, so you plug this operator between two random vectors, and the overlap of two random vectors, whatever you do to them, right, unless you ideally rotate one to be parallel to another, right, is exponentially small in a system size, right? Sorry, it's not exponential. Is 1 divided by the dimension of the matrix. You take a square root, right, and you have this overlap. Or in other words, if you want, another kind of justification for this may be that these operators obey a sum rule for some very simple operators. For example, I take my O equals sigma z, right? Let's say 1, and then I can do magic, right? I can say that alpha sigma z 1 squared alpha is equal to 1. So sigma z is a magic matrix, right? It squares to 1. But then it is equal sum over beta alpha sigma z1 beta sigma z1 alpha, right? Equal to sum over beta alpha sigma z1 beta absolute value squared, right? And then you see that you can, of course, you have a special term here, alpha equal beta, which is going to be this diagonal guy. But actually, at high enough energy densities, you don't expect your diagonal guy to be large, right? And then all of the diagonal guys must sum to 1 by this thing. If all of the diagonal guys sum to 1, and if they are narrowly distributed, right, that's kind of what they must be. Right? They must be 1 divided by, their magnitude must be 1 divided by a square root of the total Hilbert space dimension. So does it make sense? Again, maybe I'm somewhat cheating here, but in some sense, right, this term is, to me, the easiest to understand because it comes from a random matrix, right? If you do the random matrix theory, again, I can write it explicitly. OEMN in the random matrix case would be, again, some average, O delta MN plus, okay, this is going to be O average squared divided by D, and D is the dimension of my matrix, and then here would be RMN. And RMN would be some, again, random number, and there is, again, 1 over square root D hanging out in the matrix elements of, now, again, what is local operator in the random matrix theory? It's a good question. Some normalized matrix sandwiched between two eigenstates of a random matrix, right? All right, so then, yes, yes, yes. So yeah, the idea would be that you reach this expectation value, right? But you ask what are your fluctuations around this expectation value, right? What can you say about them? Maybe even at some very long times, right? If you don't do this averaging, if you don't really do the integral, there should be limit t to the infinity, right? If you don't do this integral absolute to infinity and do averaging, right? And you just do something experimentally reasonable. You wait for time equal 100 and start observing your system and asking how much is O deviating from this prediction, right? If you assume this and that, you can bound it to be decaying with a system size in thermodynamic limit. And that's something I don't have time to cover here, but if you are interested, there is a very beautiful review by Alessio, Rigol, Polkovnikov, and others, which kind of covers this whole ansatz and actually derives all these bounds. And of course, you can also look into original work by Srednitsky. So far so good, right? But as I said, right, ETH is in some sense random matrix theory plus extra ingredients. And again, one interesting ingredient which I don't have time to cover is this guy. It's an energy structure of a matrix element, right? And that comes in some sense from a more complicated structure of my Hamiltonian, right? It's not just a random matrix. It's some sum of local operators, tensor products. And this guy is actually interesting because it will know something about, potentially it will know something about the transport in your system, because again, of diagonal elements of matrix of the diagonal matrix elements of operators then can be related to a transport and some return probabilities. So in some sense, this is an interesting object, and it's a kind of it's a really different object which wouldn't exist here in RMT. So now, again, as I said, statements of ETH you can be viewed in a very crude form as a Hamiltonian being a random matrix. Of course, not in your physical basis, right? Your physical basis Hamiltonian is nice sum of Pauli matrices, but in other kind of more typical basis, right? Your Hamiltonian looks like a random matrix, and of course, it also enjoys locality, and people are doing a lot of research and trying to understand, let's say, what locality would imply for, say, higher order correlators of these matrix elements and other properties. But from ETH, right, we can have some properties of eigenstates. And I'm not deriving them, right? But one property which is you naturally obtain, right? You obtain extensive entanglement. Just again to have a full definition, you have my fermionic chain, right? I cut some region, call it region, say A, right? And I start studying its quantum density matrix, space B. That's my quantum density matrix. And now, again, all observables would be obtainable in this region by tracing my O with this density matrix, right? And again, I want these observables to be agreeing with the thermal density matrix. So natural thing is to say that this must be close to my thermal density matrix. And we know that how thermal density matrix looks, right? So for example, at t equal infinity, or beta equals 0, right? Rho A must be matrix, identity matrix normalized by dimension of a Hilbert space of A, right? So dA here maybe naively 2 to the LA, right? Some spin half without U1 conservation. And now if I plug this matrix in the definition of my von Neumann entanglement entropy, right? It's basically minus trace rho A log rho A. I'm going to recover that it's minus some lambda log lambda I, right? And from here I have minus, I have dA eigenvalues, right? They're all 1 divided by dA. And I have here log, or natural logarithm, 1 divided by dA, right? And basically, if again dA is 2 to the LA, I have LA log 2. That's entanglement entropy of my eigenstates, right? I'm asking what is entanglement of a given subregion in an eigenstate if I believe in ETH, right? And if I require that my eigenstates obey ETH. Now again, this is a lot of entanglement, right? That's called volume law. It's proportional to your system size, and it's not only a volume law, it's also a volume law with a given prefactor, right? Again, at beta equals 0, there's going to be, log 2 times L. I believe that Marcos told you a lot about corrections here, right? So if you should be careful that your subregion A is vanishing fraction of the whole system. If it's not, you'll encounter some corrections on top of this answer, right? But otherwise, this is true. And yes. Okay, sorry. Okay, yes. Yes. And now, right, again, just a reminder, this has nothing to do with the ground state physics, right? Some of these chains can still have, gapped or gapless ground state. They may have, if they have, for example, gapped ground state, right, they would have area law entanglement. they would have S von Neumann be constant, or it's not going to scale with my subregion size, right? But again, this is all behind the brackets, right, outside of the scope of this lectures, except that soon we'll encounter this area law entanglement in localized system. Right now, again, I'm not doing kind of extensive derivation of all ETH properties, right? And some of them, right, would include sensitivity to perturbations. And with this, actually, I come kind of back to the remark that why this matrix element is so small. It's actually not too small if you think, right? It's being 1 over square root of a Hilbert space dimension, whereas many body level spacing, right, is scaling as 1 divided by a Hilbert space dimension, right? So magnitude of this off-diagonal matrix element is actually parametrically larger compared to the many body level spacing, right? And you can use this, right, as an intuition for why ergodic systems are, again, in some sense, people would think about ergodic systems as an analog, right, of chaotic systems. But now in the quantum many-body setting, right, and these systems are expected to be very sensitive to perturbations, right? And that's exactly you can see what you can see already from here, right? If you're inserting some weak perturbation, right, its matrix elements are going to be much larger than the local level spacing. So it must mix a lot of eigenstates of my system, right? And that's, again, that's cartoonish justification of why this is similar to chaos, right? You have sensitivity to perturbations, right? You have level repulsion, have a certain type of level statistics, right? You have, again, this matrix element structure, which I explained, and again, a set of nice properties. Now, right, the goal of this lecture is to go away from that, right? And now I'm kind of trying to switch gears and ask, this is like certainly a very huge universality class. In many, many cases, when people study numerically models, right, all these properties, you can tick all these boxes, a lot of entanglement, level of repulsion, sensitivity to perturbations, you kind of conclude numerically that your system obeys ETH, right, not in a finite size, perhaps in a thermodynamic limit, and you kind of say, yeah, this guy also thermalizes. Now, what about systems which don't thermalize, right? And generally, why we are interested in MBL, right, in many-body localization, because it gives a route of escaping this thermalization, but everything starts with Anderson localization. Right, and models actually that I wrote there, they're also suitable for studies of one-dimensional Anderson localization. You just have to put interactions to 0. You put V or you put JZ or both of them equal 0, right? And you're obtaining essentially models of free fermions, right? And you need disorder in those models. And by disorder, now I want to do epsilon I. Usually people like some box distribution. Shouldn't matter too much, right? So EI, which used to be, or HI Z's, right? Again, for those who, as a reminder, right, I'm speaking about this Hamiltonian, fermionic Hamiltonian, and spin Hamiltonian, right? So now I switch off interactions in them and make energies random. And I now dealing with non-interacting models. One particle is enough, right? So now you can ask what's happening to these models, and in 1D, as you know, even tiny disorder localizes you, right? But just to give comparison, at W equal 0, there is no disorder, and single particle eigenstates are going to be Bloch waves, right? They're going to be labeled by some dispersion E cosine A, where I put lattice constant to 1, right? And my Y functions are going to look make it real. Psi of x is going to look some Bloch wave, and you may think, right, about at least intuitively, right, that the particle explores the full system. In a finite size system, right, there would gonna be finite probability finding particle everywhere. Now you switch W bigger than 0, right, and in 1D with truly random potential, you must have localization, right, and something drastic happens to your eigenstates, right? So now W becomes bigger than 0, and suddenly your eigenstates start behaving. Right? They start having exponentially decaying overlaps, right? My psi x, right, is gonna have here decay as e to the minus x divided by 2 psi, where xi would be some sort of localization length, right? Okay, I'm not gonna derive this very rigorously, but actually there is a very nice, elegant way of seeing this, right, from a so-called transfer matrix approach. If you write your Schrödinger equation, right, for a single particle wave function, now I have ui being my single particle wave functions, right? It's going to be ei ui. These are random chemical potentials, right? Now I need a hopping. It's going to be ui minus 1 plus ui plus 1, right? And set of ui's, I equal from 1, say, to L, or in an infinite system, right, is my wave function, single particle wave function. I just need amplitudes on a given lattice side, right? Very easy Schrödinger equation, right, written in a discrete manner. That's my kinetic energy, hopping, potential energy. This is an energy of my eigenstate, right? Now I can do a bit of juggling here, right, and write ui plus 1 to be epsilon minus epsilon I divided by e ui minus ui minus 1. And I'm expressing next one via two previous ones, right? And that can be written in a compact matrix notation. That's my transfer matrix now. And this transfer matrix hits my wave function at two previous sites, right? I have a wave function at two previous sites, and wave function at the shifted by 1 is obtained by transfer matrix. This guy has straightforwardly 1, right? There is a 1 here, and the other one just encodes this relation, right? And they have to put divided by t here. Does that make sense so far? Right, and now again, it's a nice kind of matrix, right? Let's call it M, and determinant of M is equal to 1, right? So it has one eigenvalue bigger than 1 in amplitude and one eigenvalue smaller than 1 in amplitude. And there is a result by Furstenberg, which says that in the thermodynamic limit product of such matrices under very, very generic conditions, it's going to be exponentially blowing up, right? So, okay. So what you see is that limit L goes to infinity, 1 over L log trace M1 ML is equal to some psi inverse, which is positive. Right? And that means that you kind of can see localization coming from here, because if you think about finding eigenstates of this discrete Schrödinger equation using transfer matrix, right, you'll see that most of them will have troubles because there's going to be exponentially blowing up. Right? So you have troubles normalizing genetic states. And that's, then you have to search very carefully for a special set of energies when you can avoid this exponential blow up, right? But then in the other direction, your wave function is exponentially localized. And again, that's kind of the intuition of why you have this psi here. And in some sense, psi can be also called, very often psi is also referred to as a Lyapunov exponent in this case. So again, there are two eigenvalues of this matrix, typically E plus minus L divided by psi. right? And typical initial conditions will grow exponentially, so you need special energies, and these set of discrete special energies will give you localized wave functions. Now, again, this is kind of cartoonish justification of why this may be happening, but now these wave functions at a single particle level stop exploring the whole system, right? There is also very beautiful math with questions of how a spectrum organized in this case and in this case, right? It's continuous spectrum and point discrete spectrum and so on, but it's beyond the content of these lectures. But here my particles stopped exploring my full system. Something pretty drastic happened. Now, of course, particles don't interact here, right? I can put, again, as soon as v equals 0, I can also treat the very same model that I wrote on the second board. I can treat it for many particles in it, right? I don't have to put one particle. I can put an arbitrary number of particles into this model. But I don't expect this system, right, to reach true equilibrium because there is no interactions in it. And that was a question that already Anderson asked himself. Right? And that was the question that was about existence of or stability of localization with respect to addition of interactions. So, yes? You don't need what, sorry?
You don't need the time.
Yes, again, then you can bound at some long time, you can try to bound how far away is your local observable from this thermodynamic expectation value. Exactly. So then, yes, you can kind of, then it brings it closer to experiment. You say that you wait for some time, which again doesn't blow up exponentially with your system size, and it's enough to see that your fluctuations around this value will be decaying with your system size, I believe, in an algebraic way. So you take bigger system, your fluctuations will be more suppressed. And your bigger system, your fluctuations are going to be even more suppressed, right? That makes sense. Okay. So now, again, question of many-body localization, right, is stability of this Anderson insulator to interactions. So basically, what happens for V or JZ bigger than 0, right, to the system? And this question, as I said, was asked already originally by Anderson. I refer to this review for more references and more detailed kind of discussion, right? But by now consensus seems to be that yes, there is at least a finite range. There is a finite range right, when localization is stable interactions, right? And in some sense, ways to answer this would be this kind of trying to start in some somewhat similar way, right, to Anderson insulator in a limit of infinite disorder, or trying to do perturbation theory in hopping, right? And then some other ways are this forward scattering is used, or self-consistent Born approximation was used by Bascoli, Schuler, and Polyakov, Gorny, Mirlin, right, to show stability of localization in arbitrary dimension or one-dimensional chains, right? And then more recently, there is a proof by Imbri assuming some restrictions on level attraction, right? He calls this limited level attraction assumption, which for physicists is pretty natural. Mathematicians, I'm not sure what is a mathematician attitude towards this proof. So now, again, I'm not I'm not intending to give a long lecture about these approaches, right? Justifying why Anderson is stable to a finite range of interactions. But what I'm rather more interested, right, today is saying that, let's think, let's assume that this phase is stable, right, and maybe based on these proofs, and let's go into exploring its properties, right? So, and now we kind of go to number 3. Many-body localized phase, right? And again, even though I'm assuming I want some at least intuitive definition of what do I mean by being in many-body localized phase, because you see many-body system, right, is a lot trickier, right? In Anderson, there is a very natural definition of localization length, right? You just look at your single particle wave function, right, and ask it to be localized in your real space. Now, in a many-body system, if I have a finite density, and that is again the question of many-body localization, right? Maybe I should know these guys, right? They matter at finite particle density, right? So number of particles divided by system constant, or divided by volume of system, right? And energy densities, right? I want H divided by minus E ground state, right, to be also constant, right? Then we are in the realm of many-body localization, right? If we are not dealing, if we are dealing with two particles, right, in an interdynamic limit, or if we are dealing with states energy order 1 above the ground state, again, interdynamic limit, then we are not dealing actually with the many-body localization. We can, there's also very interesting questions. What effect interactions, for example, have on Anderson, right, system? If you switch on interactions, how do they change properties of your Anderson model? But again, these are not questions of many-body localization. Right? I want some finite density of excitations, and I want a finite density of energy. So now, yeah, as I said, right, from Anderson to many-body system, you have a bit of troubles of trying to understand what is localization, because requiring localization in a Hilbert space is actually too much, right? Hilbert space is exponentially large, and the fact that your system is localized in a normal space, right, doesn't mean it must be localized in a Hilbert space, and there is also a basis ambiguity. And the best example I have for this, right, is my, is the product state, right? Like very naive wave function, right? Again, it's a product state of all spins pointing along z direction, right? But now imagine somebody else wakes up and, has a bad mood, and he looks at it like this, and he said, yeah, I like this wave function more, and so on, right? And then he doesn't write it to you like this, right? He opens it up and hands you the full many-body wave function. And this is still a very, very boring product state, right? Most boring wave function ever you can think of. But if in a many-body system you open up all these brackets, right, you're going to have exponential number of coefficients. And recognizing that this is a product state, right, it's not obvious, right? So you may think this is localized wave function on a Hilbert space. It lives exactly on one configuration in my chosen basis, but this is also localized, right? But if you expand it, it doesn't look at all localized. So again, in some sense, localization in a Hilbert space, because of huge ambiguity of choosing your basis, and it's not a good idea, right? So we need something else, right? And in my view, the key is locality, right? In some sense, you're dealing with localization, even though many-body, right? And something that we want to take as again as an intuitive definition, right? We want to have effect of local perturbations to be local. I'm allowing to have some local deformations of my system, but I don't want them to ruin and mix up my eigenstates everywhere, like it would be the case, again, in the ergodic systems, right? Because of this very large matrix element compared to the level spacing, local perturbations are going to hybridize a lot of states. So I don't want this to be the case, right? And, again, this definitely holds for Anderson insulator, right? But now, again, for many body system, I take this as a sort of intuition of what does it mean to be localized. And now I can start thinking about, I take two MBL systems, MBL1 and, MBL2, two patches, right? And I try to connect them back into my original model, right? So I take two instances of my model, right? And now I want to connect them back. And this connection includes local perturbation, right? This delta H to make these two half chains into one long chain is going to be some local term. It's either hopping, right? C dagger left, and this would be right side. Or spin, right? So this is some local term that is sufficient to switch on this coupling and obtain chain. And once I obtain chain, right, I have my big MBL chain. One and two, right? But now by this, right, I can try to ask, how do eigenstates of this big system of MBL 1 and 2 look in terms of eigenstates of these two guys? Yes? Yes? No, I mean, right, in this particular case, I really want to kind of include everybody here. But you're right, later I will try to kind of put interactions together with but here again, it's really like, if I want to connect them, right, I need to add also this term, right? So, so now again, if I want to connect them, right, I can say that, the eigenstate of this full system, which I call LR, right, should be somehow relatable, right, to the eigenstates of left, tensor product eigenstates of R, right? And if you want some kind of formula expression of this effect of local perturbation to be local, right, the formula expression that I want to say that, of course, if two vectors live in the same Hilbert space, I can rotate them, right? I can rotate them into one another by some unitary, right? But that would be the case always, right? Even if I have some most ergodic systems here, I can still rotate them by some unitary, right? So the key is the property of this unitary, right? And I want this unitary, right, to have support only on a certain distance around the boundary, right? So this unitary needs to have support, say, along distance of order psi around the boundary, right? And that's kind of the formalization of the expression of effect of local perturbation is local, right? So I'm adding local perturbation to my eigenstate, right? And I want this to be still an eigenstate, but disturbed, of course, but this radius of disturbance I want to be a finite. And then again, that's not the case in an ergodic system, because this matrix element suffices you to couple exponentially many eigenstates, right? So there would be exponentially many eigenstates coupled when you do the same thing. Ergodic system, and that's people also studied this in numerics. What you'll find that eigenstates of these joint systems, they would expand over many, many eigenstates, and by no means you can require this U. I want U to have support. U has support at distance psi around boundary. Right? Yes? again, that's this right? Again, this is very generic, right? This can be done for any system. Now this, right, is kind of a formalization of this effect of local perturbation is local. So I added local perturbation, and I must be able to fix it by some unitary which doesn't disturb degrees of freedom far away, right? So that's kind of, again, this is intuition, this is for if you wish, formalization. So does it make sense? Yes. Yes. Exactly. Then you can still do this, but U is going to be terrible unitary, which is going to have support everywhere. Sorry? Yeah, spatially, yes. Yes, so that's the difference, right? Again, so again, MBL, maybe it's a good thing to emphasize. MBL, and now ergodic, or ETH, U is non-local. Non-local everywhere. And acts everywhere. Right? That's kind of, all these things, yeah, two vectors can be rotated into each other. But this is the key difference. Right? And again, in some sense, I'm not deriving here many by localization, right? Just as a disclaimer, right? In some sense, if you wish to understand and kind of persuade yourself more that this unitary indeed exists, right? I refer you, for example, to the work by John Imbri, right? Who really tries to build such a unitary for one specific model, right? In a limit of strong disorder, what he does, right? He tries to iteratively diagonalize your Hamiltonian and builds this operator which diagonalizes your Hamiltonian. And in some sense, he doesn't build exactly this unitary, but he's building the unitaries that will be on this board in 3 minutes or 4 minutes, right? But what I'm interested in this lecture is more introducing this phenomenology or introducing description of many-body localized phase and then exploring kind of measurable, observable consequences of this phenomenology or of MBL. And actually, yeah, by the way, right, what I'm doing here, you can see that this is synonymous to area law entanglement, right? So area law entanglement is kind of already built into my system, right? Because I have a product state here, and I say that I act on it by some unitary operation which has non-trivial action on a finite range around the boundary, right? So I can entangle only degrees of freedom where this unitary has a support, because I'm starting originally with a product state. So that's kind of it, right? In some sense, this would also imply area law entanglement of eigenstates. But again, saying area law entanglement of eigenstates is one thing, but what I'm gonna hopefully get, right? What is the dynamics of MBL phase and what are other properties? Because eigenstates are hard, if not impossible, to observe and prepare, but dynamics is something that experimentalists do routinely, right? So now, again, as I said, implies area law entanglement. And that's already kind of, maybe not unexpected, right? But pretty surprising because this is entanglement of not just a ground state, right? But this would be if you are many-body localized, and here I'm dealing with only so-called fully MBL system, so I don't assume that there is any mobility edge there or anything like that. So all eigenstates are localized, right? So of all states, right? Including highly excited. Of all eigenstates, sorry. So now, again, this is construction that you kind of try to extend in a bigger, by making more copies of this MBL, right? And make the case that the system has local integrals of motion. That was kind of my original kind of construction that was proposed in something like 2013. I think around the same time, David Hughes and others, they came with very similar construction, but they kind of brought it to the level of a single spin. And if you bring it to a level of single spin, then actually formulation becomes a lot more elegant. So now, using similar type consideration, I want to construct conserved quantities, or this quasi-local integrals of motion, right? And for this, I actually, again, I'm doing very similar construction, but I'm bringing my size of the systems, MBL1 and MBL2, to a single spin. So I take, I take my spin chain. I like a bit more doing spin chain, just because there is no need to think about any signs and any statistics here, but the same thing can be done for fermions, right? And I can write, right? And now I indeed can take interaction as a part of my H node. So my H node would have sum of HI sigma ZI plus sum of JZ sigma ZI plus 1. And that's going to be my H node. And all these states are an eigenstates, right? Any product state is an eigenstate of such a Hamiltonian. And I am putting this here just because it's also diagonal. It doesn't matter, they're all eigenstates anyway. Now I want to go from here, right? I want to treat this H perp or H hopping as a sum of local perturbations, right? That's going to be J perp, sigma plus I, sigma minus I plus 1. Right? I want to treat, in some sense, I want to repeat this construction, right? Here somehow, at least, kind of, maybe it's a bit easier to think about it, right, as taking some big systems and then adding some local perturbations, right? Here I really, again, want my systems to be of one spin size, right? And then this is kind of a sequence of local perturbations, right? And I'm not gonna, in some sense, again, I'm not deriving the existence of localization, right? But I'm just relying on its existence and on ability, right, to bring these eigenstates into exact eigenstates of H plus H perp, right? Again, I want to have H node plus H perp, which is my H spin. Right? And now these are going to be some kind of not a product states, right? These are going to be some many-body eigenstates. So I'm drawing these things to show some sort of entanglement in them, right? They're entangled. These are exact many-body eigenstates, right? But if I kind of repeat this construction, right, and if I say that effect of this sum of local perturbations is still local, right? The idea is that I can obtain these eigenstates of my spin fermionic chain as a sequence of quasi-local unitary transformations, right? Here I just needed to apply unitary transformation to fix effect of one deformation, right? Now it's not going to work because I added kind of a sum of local perturbation everywhere throughout my system, right? But the idea is that if I take from this, I call it sigma. So I start from this eigenstate of the Hamiltonian without kinetic term, which is some product state, right? So what I can do, right? I can start first by applying unitary, and here I'm using some tensor network type notation, right? I'm start applying two-side unitary, right? I need 2 layers of these guys. And then I start applying 3-side unitaries. And so on, right? So, again, if you think about this unitary circuit, right? Again, that's my U, right? And I want this U to give me alpha, right? Which is an exact eigenstate of this H naught plus H perp. So my alpha is an eigenstate of spin, say, Hamiltonian H spin, right? So that's the structure of my unitary operator. And again, the key everywhere here is locality of this operation, right? It's not the existence right? Again, I want my alpha be u times this sigma z, this kind of product state, right? But again, the main thing is that this is always possible, right? You can always write any state in the Hilbert space as a unitary acting on a given vector. So it's not a surprise, right? The crucial thing is in the properties of this u, right? So now I want this u be quasi-local. And by this I mean, again, that I want it to be a product of u2, I plus 1, and so on, right? Then product of u3, and so on, right? So I want my unitary to be decomposable into such things, and if you want some specific thing, I can assume that these higher unitaries, right? They have some norm which decays exponentially with their range, right? So these unitaries, the further I go up here, the more and more these matrices are resembling identity matrix, right? Which does no operation, right? So I want higher and higher layers of this guy to be decaying or to have decaying norm, right? So now this is the key point, right? If you wish, again, this is also to the best of my understanding, right? This is something that is achieved in a proof, right? For a specific model when the diagonalization proceeds iteratively, right? And you want to diagonalize your system, right? You want to build from something very simple, from a product state, you want to build an exact eigenstate, right? But you want to build it not just by sticking it in a computer and asking it to spit you out the result, but you want to think about locality, right? You want to maintain locality, you want to maintain a memory of who comes from where, right, in this process. So now if you have this construction, sorry? Well, okay, by any realization of disorder, I guess one has to deal specially, right, with some potentially more delocalized or like rare regions, right? In principle, indeed, you may have some, if you think about Imbri's proof, right, when he does this diagonalization iteratively, there are some regions when this diagonalization fails in the perturbation theory, right? And then those regions have to be dealt with specially. But the key, right, is that you can prove that there is, these regions are not important, right? Or these regions occur with, I believe, exponentially small probability. It's that it's not, if you take some normal realization of disorder without fine-tuning it, of course there is a realization of disorder when there is no disorder. It's also realization of disorder. You can have random numbers, right, spitting you out all zeros in principle. But yeah, of course, the question is what is typical or what is average realization is doing. And again, there I believe that the proof proceeds by treating some regions which may exist, which may be kind of more delocalized or where this procedure stops working, but those regions are are small, kind of, or are rare. They don't have to be small. There can be probably also even very big regions, but there would be even more rare, right? Yes. Yes. No. Here you see again, there is a first layer of pairwise, second layer of pairwise. Then the third layer would be three-side. Then you need 2 more layers to make it generic. Then you need four, and so on. So again, there is as I write here, sorry, maybe it's not clear. There is pairwise, triple-wise, 4-spin unitaries, and potential, right? Again, the idea is that you are allowed to go up to the entire full size of your system, right? But the condition is that the more range you have, more similar it must be to an identity matrix, right? The difference between identity matrix and this humongous unitary which acts on the full size of your system, right, was going to be exponentially small in the size of your system. Make sense? All right, so now kind of we can now try to start with these guys, right? And we know that the eigenstates are obtained by dressing them by quasi-local unitary, right? So we start with these guys. And what we are going to do, right? We're going to, for example, consider some, some eigenstate sigma prime, right? Write sigma z here. Take another eigenstate sigma in the product state, right? And now I'm going to apply u and u daggers everywhere there. So I'm applying, right? I'm applying basically sigma prime. I'm applying u dagger u. Now I have sigma z. I'm applying u dagger u here. Applying sigma. And by this, right, what I'm obtaining this would be now rotated. Right? It's going to be eigenstates of my exact spin chain, right? My XXZ spin chain, if you wish. Right? There's going to be some alpha prime. I'm going to have operator u sigma z u dagger, right? And I'm going to have operator alpha. Sorry, eigenstate alpha here, right? This makes sense, right? But here it looks trivial, right? This is just sigma z, and these are product states in the sigma z basis. So this operator, all these states are eigenstates of this operator, right? Now I kind of rotated everybody, right? And now this guy rotates into operators that I call tau z, right? Tau zi is going to be this u sigma z I u dagger, right? And all eigenstates are still, all exact eigenstates are eigenstates of this operator. So this is an integral of motion, right? But, and again, the surprise is that in the many-body system, you can always construct integrals of motions by taking projectors onto your many-body eigenstates, right? That's one very kind of obvious example, right? Unitary evolution is unitary, eigenstates have the same probability, but this is very useless and terrible kind of conserved quantity. Because eigenstate is a very big volume law entangled state in your Hilbert space. There is no way kind of to compress it or make anything out of that. Right? Here, the thing is different, but again, everything comes from a structure of U, right? There is no surprises that this holds, no surprises that this holds. There is only value in it because of U having special structure, right? And again, all this tau z i's with my h spin Hamiltonian are going to be commuting, right? And this tau z's is what's going to be in David Hughes' paper is called L bits. And again, I'm calling them LiOMs. Because if you have L bits and then normal guys are called P bits, L and P. I find it more conventional just to call them LiOMs, not to be confused who is L and who is P. And now from structure of U, right, there is a certain structure of this tau z. So I expect this tau z to be some sigma zi, right, plus sum of right, and I'm organizing my so-called operator expansion. Again, it has nothing to do with operator expansion in some field theories and conformal field theories, but it's still expansion of one of this integral of motion, right, in the basis of my sigmas. And there is a bit of abuse of notation, right, because these sigmas are not the same sigmas as would be in this would be working in my H spin, right? So this expansion again of this tau z really over spin operators, right? These are my physical spin operators. Right, and now again, I want if my all unitaries are exponentially decaying, what you can see, right, that this tau z must retain some of its local structure, right? It stops being exactly local operator, right? But it retains some of the local structure, right? It has a finite overlap with, let's say, spin at a given site, and then it has this sum, and by On, I want, O1 is gonna be some sum with coefficients is gonna be, sigma z, let's say, if it's I, right? If I don't know, if I have, for example, I equal 1, it's gonna be sigma 0, sigma z1, then it's gonna be sigma z minus 1, sigma z0, sigma z1. Sorry, something. 0, 2, right? And then it has some sigma plus, sigma minus, say 0, sigma minus 2, and so on, right? So it includes all possible operators of a certain range. So again, I have some spin I equal 1. So this is going to be range of my O1. This is going to be range of my O2. This is going to be range of my O3 and so on, right? So again, O3 is allowed to be some superposition of these operators. And now I want it still to be normalized, right? So then if my O's is normalized, then the all spatial decay is encoded in this guy. Right? That's just more convenient for notation. If you don't require them to be normalized, you would have a slightly different decay, but these coefficients, right, the decay is e to the minus, I think, 2n over xi. Right? That's something that I would call operator localization length, right? And there is some length scale xi, and as you'll see, there is a bit of a mess with length scales in this phenomenology, and actually setting and understanding indeed how many different bled scales there are. It's a good, very interesting research kind of question. And again, I'm not sure if that can be addressed analytically, but certainly numerically one can try to address it. That's again one of the interesting open questions of kind of come and carefully understand if one length scale is sufficient, or if really you have a many-body localized phase really needs a multiple number of length scales to characterize and describe it. But anyway, so this is kind of expansion of my tau z over spins. And now what I want to say, right, is that my Hamiltonian must, expressed in the language of tau z's, may include only, expressed in tau basis may include only tau z's, right? Because taus can also form a complete basis. I can write tau plus and tau minus, and these operators are going to be just exactly connecting given number of eigenstates, right? I can also dress them by U and still obtain the same expansion or very similar expansion, right? But now Hamiltonian H spin in tau basis, right? Since all tau z's compute, right? It must be Ising type Hamiltonian, right? That's what people call the Hamiltonian of HMBL, right? And it starts with a leading term, which is some H tilde, tau z i's, and then you have two spin terms. You have three spin terms. And so on. And okay, let me make I bigger than J, I bigger than J, bigger than K to avoid overcountings here, right? And now you can think of this guy, right, as taking these quasi-local expansions, right, inverting them and plugging into H of XXZ spin chain, right? And what's happening there, right? That XX exists, Hamiltonian of my spin chain has only two body terms, one body and two body terms, right? So it's strictly local. Now I'm inserting my expansion of sigma z versus tau as something quasi-local, and I'm getting all possible terms, but these terms also must inherit exponential decay, right? So the idea would be that this Jij proportional to J naught, E absolute value I minus J divided by some other length scale, I call it kappa. And again, you can put relations between, let's say, this length scale and this length scale, but these relations would necessarily include some assumptions about statistics of expansion coefficients and other assumptions. And since I don't know, right, if these assumptions are true or no, and in localized systems, very often one deals with broad distributions, right? You know, I prefer to keep them as a separate length scales, right? And the homework is to write a paper which relates all these length scales together, right? So this would be J naught E I minus K divided by kappa, because J, you know, this is a range, and so on. Right? So I'm assuming that all these guys are exponentially decaying. Again, if you want to discuss kappa versus psi, again, the intuition is that there may be a bound, something like this. Don't want to discuss. There's some entropic factor in it. Right, and in principle, if this psi diverges at the transition, then again, I would expect that this guy still need not to diverge, this guy still may be constant. Right? But again, that's something of a more speculative nature. So now we arrive to this Hamiltonian of MBL phase, we arrive to this local integrals of motions. Root is not unique, and that's kind of nice, right? If you like unitary transformations, you may do what I was trying to show here, right? If you are a fan of RG, right? If RG is your best approach, right? There also exists RG approach. So other approaches, LiOMs, and one approach is going to be RG, right? I think it was Wosk and Altman who pioneered RG for dynamics, and then later of excited states, and then later you want to reference it's Pecker, David Pecker, and others, right? Who generalized strong disorder RG to the many-body localized systems, and the idea, right, is that if you in a strong disorder RG, right, you find, let's say, spin with the biggest magnetic field, or two spins with the biggest exchange, right? And you perturbatively, you diagonalize this block, right, and put them usually in a normal RG. If you are after ground state, you put them in the lowest state, right? If you find a spin with a very big magnetic field, you put spin parallel to the field. That's the lowest state of the spin. Now the idea of this RG, if you want, what you are doing, right, you are allowed to do otherwise. You are allowed to take a spin in the magnetic field and put magnetic field opposite. Right, and then you are not the lowest state of this spin, but you put it into a highest state. And then you proceed, right? Of course, it's challenging to show, right, because ground state is unique, it's challenging to show that on this branch of RG process, you don't encounter resonances, because something that may happen that at some much later stage, there's going to be potentially some resonance, because you are now in the many-body system, you are in a continuum, you are in an exponentially dense part of the spectrum. But if you believe in this process, right, it would give rise to similar type of local integrals of motion, right? Because you glue your two spins, for example, into some state, which is not necessarily ground state, and then you leave it there, right? It stays there throughout your RG process, and that's also your effective integral of motion. Now, RG is going to produce integrals of motions, not like these guys, which are kind of all local. It's going to produce integrals of motions bigger and bigger scale, right? There's going to be like Russian doll construction in the sense that you start by integrating, maybe individual spins and pairs of spins, but then in the next step, you may encounter already a spin which was kind of effective spin, right? Which comes from some spins integrated out previously. So in that sense, there is a certain locality to this integrals of motions, but it's a bit more kind of proper locality to the systems with criticality, right? So that's, sorry? Yes and no, right? I think, yeah, I'm not sure if how much you can do analytically in this process, because in the end, you have this exponentially large tree, right? And I believe in the end they resort to some sort of Monte Carlo type sampling of the processes on this tree. So in that sense, I would say it's probably more numerical, at least as, you know, for the kind of practical extraction of some quantities. Because you're dealing with highly excited eigenstates, and then you have to do kind of some sampling. Should I stop, or can I use one more minute? Okay. Yes, just one more thing, right? Another way would be some sort of extensions, right, of works by Pasqualini, Schuler, and Mirlin, right, and building this quasi-local integrals of motion in some sense perturbatively, right? That's something that was done by Scardicchio, Ross, and others. Ross, Müller. Scardicchio, right? It's again, it's kind of extent self-consistent Born approximation, and get dressed, let's say, fermionic operators, right? You get your fermionic operator expressed in a very similar fashion, right? You know, you would have C is equal to Z C I plus all other higher order terms like here, right? And there is some way to build this expansion. And of course, there are numerical constructions. And it's also still, I would say, there are algorithms, many algorithms on the market which kind of try to build this LiOMs, but there is still a lot of open questions. There is no probably proper killer algorithm which would make this problem kind of treatable, let's say, for a much larger system sizes, right? Because that's something that you eventually would hope, since you are localized, since your eigenstate have very low entanglement, maybe, you know, dream algorithm should be able to construct your eigenstates of, you know, hundreds of spins and do it with some extreme precision. And I think it's still not around. So feel free to contribute. And at this point, I'll stop and we'll resume after a coffee break. Thank you.
Very good. Thank you very much. There's time to take some questions now.
Excuse me? So you want a reference, or? Okay, I'll write it. Well, let's not do it now. I'll write it by the beginning of the next lecture.
Okay. Are there any questions? Yes. Mm-hmm.
You try to repeat this argument for the transfer matrix for Anderson. Can you do it? Order?
Well, but for Anderson, right, you know, it's, you know, remove all these terms, right? It's kind of also there if you wish, right? This construction, it holds for Anderson. You just remove all these terms, right? And also these type of expansions will also become a lot more special, right? So in some sense, yeah, Anderson is included here as a particular case because you can take a many-body localized phase and, you know, switch off your interactions, and all this description is expected to hold. But again, I think Anderson is in some sense, Anderson's later case is simpler, right? Because, for example, here you have just Anderson orbitals, right? Energies of localized states, and that's end of the game, right? Now here you have all these higher order terms, right? Likewise, does it make sense?
Suppose there is a transition. So can I see this transition starting from your MBL? How do I see it? All localized?
Well, you know, you should start. That's exactly, yeah, that's also a very good question. So it's the question, like, generally we hope, right, that at the transition, there may be some divergent length scale, right? And I already draw 2 psi and kappa. I'll write, you know, few more letters with its primes and other things, and the question who is diverging, right? Who is not, and who is responsible, right? In some sense, if there are several of them divergent, who is kind of the most fundamental or the best way to define localization lengths? And to be honest, right, the very short answer, I don't know, right? More speculative answer is that intuitively, right, in this process, if you come closer and closer to the localization transition, you should start encountering difficulties, right, in building these unitaries. There should be progressively bigger and bigger regions, right, where this unitary is gonna violate, or this length is gonna become larger and larger, right? That's kind of the cartoon picture, and that's something that people call resonances. Now, how they are organized, you'll hear tomorrow you'll hear some RGs about resonances, right? But actually taking some microscopic model understanding how these resonances are organized there is still has not been achieved kind of completely, in my opinion.
Okay, any other question? Please.
So a question related to the previous questions. Imagine there is a mobility H. Yeah, I know some people
Yes.
question this, but if they are still, so but if it still exists, but you are in the many body localized phase, however, at some high energy there is a delocalized phase. So what happens with all this formalism of local integrals of motions? So it's in some way it should reflect the fact of existence of the many body localized phase. On the other hand, there is also delocalized. So what would it mean?
My understanding is that at some point, some people tried to extend this construction to the case of mobility H by presumably adding projectors. So you can try to think that maybe this whole thing kind of still works, but please project it onto energy density below certain, right? That's kind of would be a hypothesis, right? And very speculative one. So that's kind of one hypothesis. If that's the case, or if this whole construction doesn't exist, I don't know.
Okay, very good. Other questions? Yes.
Hello. So in an ergodic system, as the eigenstates are quite non-local, so the projectors will also be non-local. But in MBL system, as the eigenstates have this subthermal entanglement entropies and all those, so are the projectors of the eigenstates have also local structures? So isn't this whole construction of local integral of motion isn't some sense equivalent to taking just projector of the eigenstates?
Yes, I think it is. Again, that was also part of the original justification. So I think, at least I was originally thinking about these LiOMs as living in some bigger chunks, right? And then trying to construct LiOM as a sum of projectors in this case, right? And showing that the sum of projectors can be made local, right? So in some sense, you're correct, right? It's a bit less, again, to me, it's a bit harder to justify in a case when, all spins are all subsystems are treated just in form of individual spins. But you're correct, right? Yes, that, projectors on eigenstates would form a complete basis, and they have, a set of LiOMs which also form a complete basis. So idea would be that in MBL case, you can find certain sums of projectors onto eigenstates which are going to give you quasi-local operators.
Any other questions? Well, that doesn't seem to be the case, so we will come back at 11:30 to this lecture hall.